Okay, we're going to do some more moments of inertia, beams and bending, shear and bending diagrams, flexural stress, all of that. We're just going to do it all in one problem. And I thought today what we would do, it'll be similar to last time, but with different geometry. So this time what I thought is we would take our T-beam, or one that we'll come up with some dimensions for, one of our own, and instead of creating just more complex geometry with the primitives that we have, like the rectangles and triangles and all that, we're going to take an existing beam, a channel beam or a C-beam, and put it on. This isn't a channel, this is just flat, but it represents our channel. Glue it, weld it, whatever, fasten it on top of our T. So we're going to use one piece that we need to look in charts to get the data for, and another that we will provide our own set of dimensions for. So let's go about drawing what I'm talking about. Something like what I'm talking about anyway. So here's the channel. If we're looking at the, the end of the beam, well, there, the end of the beam. Something like this. It's got some kind of thickness to it. And it'll have the channel pieces sticking up this way. So something like this. So this will be a regular channel that we can look up material properties, well, not material properties, but sectional properties for, like from here. And we can make it one of these known beams. We're going to use a C10 by 30. So I'm going to write that down. We're going to go ahead and grab some of this data while we have this open. So C10 by 30. We need the area. If we're going to do parallel axis theorem, one of the things we need is the area. So C10 by 30 area is 8.82 square inches. We're going to need, well, we don't need it, but this width of the flange, that talks about, the distance, how far these little flanges stick out. And it says for C10 by 30, that's 3.03. I'm going to call that dimension H, just because I want to label it as a variable in our picture. So 3.033 inches. We don't necessarily need the flange thickness or the web thickness. We do need a moment of inertia, but we have to be careful here. I have oriented this flange, the T, haven't drawn it yet, but the T is going to be down here. And so this is going to have loads when I build my beam. Here's the channel, here's our T. I'm going to build it this way and put the loads here, somewhere over here. So the way that the chart has the information, it has the channel rotated 90 degrees clockwise from that orientation that we're actually using. So the loads are actually going to be parallel to the x-axis and perpendicular to the y-axis. So I need the perpendicular orientation. I need the axis YY data, which says that the moment of inertia for a C10 by 30 is 3.94 inches to the fourth. If I wasn't careful about that, and I used the XX like I normally do, I would have used 103, so 30 times more than I needed to. I also need that distance now, and here they call it X sub C, but again, our orientation is 90 degrees from this one, so we are going to call that Y sub C, and it is C10 by 30, 0.649 inches. So all of this data we just get from a chart. We don't have to go and measure the channel beam or anything like that. We can just look up that piece of information. So let's go back over here. Let's put the T in our beam. I'm going to just kind of put it underneath here. I want to make it a little bit narrower just so it stands out some. something like that. It's not particularly important how we draw. Whoops, I'd like to draw it straight though. All right, so here is our, just to separate them a little bit, channel up here, welded or glued, or somehow it's fastened to, and it's pretty, solidly fastened. They're going to operate as one composite beam. So there's some kind of little welds in here or whatever. We're not analyzing what's going on at the actual weld. That would be this interface between the channel beam and our homemade T-beam would be a good place to analyze that shear stress between the layers. We kind of did an example of, we had a book and bent the pages and how the pages might want to slide past one another when they bend. That would be a good place to analyze that shear stress. We're not doing that. That's a different shear stress. It's not the direct shear V over A type shear stress. But if you continue studying mechanics and strength of materials and beams in particular, you'll get to the shear stress between these layers. And it's not a difficult equation, but it's not one we're working on today. All right, we need some more dimensions on here to fill out our T. So let's say that I don't really like putting this dimension up here, but I don't have a better place to it. So this is the width of the flange for the T. We're going to call that 8 inches. We're going to call the thickness of the flange of the T. We're going to call that 2 inches. This is H. This distance over here came from the chart, 3 inches. We'll call the entire height of the stem, got that a little crooked, that's going to be 10 inches. And then we'll have this width down here, we'll put that at 3 inches. Okay, I think that's all we need. That really bugs me how crooked that is, but oh well, it'll be all right. So the first thing we have to do is we have to figure out where is the neutral axis for our composite shape. So that's the centroid of the composite shape, basically. So we have 3 pieces. We have the stem, we have the flange, and we have the channel. So let's get to work with our chart to create a idea of where the centroid of our composite T channel beam is. So shape 1, I'm going to make that the stem. Shape 2 will be the flange, and shape 3 will be the channel. Right? So they each have an area. For this, it's 10 by 3 is 30. Here, 2 by 8 is 16. And then we don't have to calculate this area. We have it from the chart, 8.82. So we just take that 8.82. I was going to write inches squared, but I put it up here, so I don't need that. And now we can get our total area just by adding these. 30 plus 16 plus 8.82, 54.82. Okay, I realized I didn't write my coordinate system in here, so I'm going to put a reference axis down here, and then we'll put the y-axis right through the center, like that. The centroid for each one of these pieces, part 1, the stem, is right about there. Part 2, the flange, is right about there. Part 3, the channel, is somewhere up here. Might be even floating in midair there. And we're looking for the neutral axis, which should be somewhere in here. We don't know exactly where, but it should be somewhere over here. And that's what we're looking for right now with this centroid. All right, so we need to measure from our reference up to the distance to each one of these individual centroids. So for part 1, it has the whole rectangle is a height of 10, so that's just 5. Part 2, we go from here 10 plus 1, so 11. And here we go 10 plus 2, 12, plus this distance which we got from our chart, 0.649. So this is 12.649. And then we multiply A times Y to get the first moment of area, the numerator for our centroid equation. 3 times 5 is 150. 16 times 11 is 176. 8.82 times 12.649 is 111.56. And we'll sum this to get our total area for our composite T-channel beam. So 111 plus 176 plus 150, 437.56. And then we'll calculate Y sub C, or the location of the centroid of our composite shape, which is also the location of the neutral axis for our composite shape. .98 inches. Okay, that seems reasonable with what we anticipated it to be. You know, we didn't have a really good idea where it was, but this seems within the realm of possibility. So we'll go with that. And so that's this distance right here. From our reference where we measured all of these centroids to the neutral axis is 7.98 inches. So that's like step 1. Now we can turn the page and go on to, we need to calculate the moment of inertia for this shape. There we go. Actually, we probably need to keep this nearby. All right, so we have 3 pieces. And we need each one, piece 1, the stem, it has a moment of inertia that's easy to calculate about its own centroid axis down here. But we need the moment of inertia of the stem about the neutral axis. So there's some distance between these two axes. That's where the parallel axis theorem will come in, is to calculate the effect of the stem about the neutral axis versus the stem about its own central axis. So let's do moment of inertia. I'm just going to draw the picture of the stem versus trying to write stem and flange and all that. So this is the stem. Equals, it's a rectangle. So if you don't remember the base equation for a rectangle, you have to go to a chart. Let's see if we can pull one up. There's a chart. There's a rectangle. And you can see that the distance parallel, or the dimension parallel to the x-axis, is labeled B. Dimension parallel to the y-axis is labeled H, and then we have BH cubed over 12, and then we also have the x prime equation over here, BH cubed over 3. We cannot use this one because that would give us the moment of inertia about the base of this piece, and we couldn't apply the parallel axis theorem to it because this equation already has had the parallel axis theorem applied to it. So the only reason we could use the x prime is if, in this case, we wanted the moment of inertia down here about the x-axis for some reason. But we don't. We want it up here at the neutral axis. So base of the stem is 3. Height of the stem is 10. So there's BH cubed over 12. Plus, we're going to have to move the effect up to the neutral axis. So the area is 30. And the distance between these two axes, this one is 7.98. The neutral axis for the entire shape is 7.98 inches above my reference. And the centroid axis for part 1 is 5 inches. So there's 2.98. Technically, it's negative 2.98 because we're going from the neutral axis down to this axis. So technically, it's negative 2.98 inches. but then we square it, and so the negative sign doesn't actually bother us there. Now we just need to do that bit of math and figure out what all these individual numbers are. 10 cubed, oops, that's not 10. 10 cubed times 3 divided by 12, 250 for the first term. And the units, inches cubed times inches, so inches to the fourth. Here we've got negative, but I'm just going to put 2.98 squared times 30, 266.4. Again, inches to the fourth power. And we add those two terms together. Whoops, not multiply. Add 250. And we get 516.4 inches to the fourth. So that's the moment of inertia of the stem only about the neutral axis of the entire construction here. All right, let's do the flange. Moment of inertia about the own centroid axis, right here. For the flange it's also a rectangle, so bh cubed over 12 again. It has a base of 8 and a height of 2. It has an area, so this axis is not at the neutral axis, so we have to use the parallel axis theorem to increase the moment of inertia of this flange about the neutral axis compared to the flange about its own axis. So an area of 16, and this distance would be this height, which was 11 minus 7.98, 3.02. All right, these terms, here we have 8 times 8 divided by 12, or let's do it all, 2 to the third times 8 divided by 12, 5.33 inches to the fourth. Here we have 3.02 squared times 16, 145.93 inches to the fourth. We add these two together and we get 151.26 inches to the fourth. This would be the moment of inertia of the flange about the neutral axis of our entire composite shape for our beam. Okay, now we still have to deal with the channel that we stuck on top of here. So there's the moment of inertia of the channel. We don't have to do this. It's not a rectangle. It's not a triangle. It is a predetermined beam, C10 by 30, where we already have the moment of inertia. We do have to be careful to use the correct moment of inertia, but ours was 3.94. So that's the moment of inertia of the channel about its own centroid, but we still need the parallel axis theorem because its centroid is up here, and we need to move it down to the neutral axis. So the area, we looked that up in the chart, 8.82. And the distance between this axis and the neutral axis is, if you remember, that was 12.649 up to the centroid of the channel. And then subtract off our 7.98. So that would be this distance minus this distance gives us that distance. And it equals 4.67. And we square that. All right, so this one is just what it is, 3.94. And here we have, well, that number squared times 8.82. 192.27. We add that to our 3.94. and we end up with 196.21. So there are the three pieces with their moment of inertia translated down to the neutral axis of the composite shape, and we can now get the moment of inertia of the whole cross section, here, just by summing these three. So I equals, and let's add them up, 516.4 plus 151.26 plus 196.21 is 863.87. This is the moment of inertia that we will use in our flexural stress equation and other beam equations. If we were doing bending or things like that, like the actual deflection, then we would need this moment of inertia for this cross section. But here it is. We're going to use it in flexural stress in this equation. But we need M. We need to know that bending moment. So now let's go over to our shear and bending diagram. Keep this number handy for future reference. But this one, let's make into a cantilever beam. So that means it's only supported at one place. It doesn't have a pin and a roller. It has a fixed support somewhere. And we'll put that fixed support on the left-hand side. I'm just going to draw a straight line to represent our beam. Something like this. Maybe like that. Make it go out there. All right. Now let's put some loads on here. If I can find a good pin for load application. Here's one. I want a red one. All right, let's put, again, it's cantilevered, so there are X and Y reactions. I'm going to say this is the cantilevered end. So this is basically like a beam that's attached in the wall, and we're going to push down on it, something like this. So over here I'll have an AY. It's possible I would have an AX if I put a load that is at some sort of, angle pushing in the X direction. I'm not going to do that, but I'll draw AX on here. And then I'll just zero it out. And then there's also a concentrated moment here. And we'll just call that the moment at A. You can call it whatever you want to. All right, let's put another concentrated moment applied to the beam. This is going to be 3 kip feet. Let's put a distributed load. This one's going to be 1 kip per foot. And then let's put a point load at the very end of the cantilever, and let's make it 2 kips. Okay. So our only reactions are over here. We need to solve for this AY and MA. I'll go over here to the side. I'm not going to use the units just so I have room to fit the equations in. If I put the units in, then the equations run off the page. So I would just write the numbers that go in here. We're going to do moments about A over here. Very first thing is there's a moment at A. It's counterclockwise. I said clockwise is positive, so that's minus moment at A. This one's also counterclockwise, minus 3. This is a distributed load, so when I'm doing moments and forces in Y, I need these distributed loads to be point loads. Oh, I need to put dimensions on here. We can't do anything until we have dimensions. Hold on. Let's go ahead and draw all of our reference lines here and put dimensions on this thing. Oh, I drew on the ruler, not on the page. And then we'll put a line across here for all of our dimensions. Let's keep them relatively simple and just say that this is 2 feet, 2 feet, 3 feet, and 3 feet. Even though they don't quite look like that, that's what they're going to be. All right, now we can figure out that we have a 1,000 pound per foot load spanning 3 feet. So it's a total of 3,000 pounds. I'm using kips, so 3 kips. And it would be set over 1.5 feet. So it's in the center of that distributed load. Is that the centroid? So if you have a distributed load that is not rectangular, you have a triangle or some other shape, then this lumped load is still the area under this curve, but you put it at the centroid of that area. All right. So this -3 was from here. Here we have positive, because I said clockwise is positive. 3 times this distance is 245.5. And then plus 2. And we have a distance of 2,410. So the only unknown here is the moment in A. It's negative the way I drew everything. So I'm going to take that, move it to the other side, and it just says moment at A equals, and we add these things up. So -3 plus 3 times 5.5 plus 2 times 10, 33.5. Now we have to be careful here. This is kip feet. But it's a positive sign, which means I drew this arrow correctly. This is a clockwise, oh no, this is counterclockwise arrow. So counterclockwise moments, external moments applied to beam. So the concentrated moments on the free body diagram up here, when they're counterclockwise, they are negative bending moments for our drawing our bending diagram. We made that assumption long ago when we started drawing those internal forces and bending moments, internal shear and bending moment inside a beam. We have to keep that convention. So this will actually be a negative step down, or a step down in our bending moment diagram when we get to that. We still need AY though, so summation of forces in the Y direction equals 0. We have AY -3 minus 2 equals 0. So AY equals 5 kip. All right, so we have all of our external reactions solved. Now I'm going to come up here, draw my horizontal line for the shear diagram, something like this. So that's where shear is 0. We're measuring in kips. We need an axis system on here. Looks like we're going up 5 and then back down to 0. So we'll just make 5 kind of right here. Whoops. Well, we get the idea. I kind of messed up my marks there. So we start at 0. The first thing that happens is we have AY pushing up at 5, so we go up to 5. Then nothing happens. The concentrated moments don't affect the shear, so the shear stays constant until we get to the beginning of the distributed load. So it just stays at 5 kip. Then we hit the distributed load here, and the distributed load is pushing downward 1,000 pounds per foot. I've got it spanning 3 feet, so it's going to go from 5 minus 3 down to 2, which is, right here somewhere. And this is a constant or evenly distributed load, so I have a constant slope. The slope is negative because these forces are pushing downward in my negative y direction. Here nothing changes until I get to the very end where I have 2 kips going down. I'm at positive 2, so that gets me to 0. So this is the shear anywhere in the beam. It doesn't have any negative sections. They're all positive. And that's usually what's going to happen with a cantilever beam. And I need to go ahead and divide it into the individual pieces. And I need to basically integrate this, so I need to calculate all the areas under the curve here. So I do need, this is why I draw the guidelines, I do need to remember this is 2 separate areas. I can't treat it as one 5x4. I have to treat it as 2 5x2s, because this concentrated moment is going to interrupt what's going on in my moment diagram, and then we'll get back to what I'm doing. So I need to break these into 2 separate ones. So 5 times 2, 10. The units would be kip feet. Same thing here. Here I've got a triangle sitting on top of a rectangle. So a common mistake that happens here is you go to calculate the area of this triangle. You say, oh, it has a height. Remember, this point is 5. Has a height of 5, a base of 3, and divide by 2, and you do that calculation. But the height of the triangle is only this far. This is the height of the triangle, which is 3. So be sure you don't miscalculate the height of the triangle when you're calculating its area. So 3 times 3 divided by 2 is 4.5, plus the 2 times 3 plus the 6 over here gives this whole area 10.5. So 6 from the rectangle, 2 times 3, and 4.5 from the triangle, 3 times 3 divided by 2. And then here I've got 3 times 2, I've just got 6. None of them are negative, so my bending moment diagram is constantly going to be going upwards. In fact, I'm going to draw it higher. Normally I draw them kind of down here, but here, this bending moment at the very beginning, this concentrated moment, is counterclockwise 33.5 kip feet. So it's going to start out as a negative 33.5 right off the bat. So I'm going to draw it higher and work my way back up to 0. So let's just say that down here is 40, negative 40. So right in here's negative 20. Somewhere there's negative 30. Somewhere there's negative 10. All right. So like I said, the very first thing is this concentrated moment at A, 33.5 kip feet, counterclockwise. So I immediately go down to negative 33.5. And then everything starts going back up towards hopefully getting to 0 at the very end. So this area is positive. All of these are positive, so the slopes are positive. This is a 10. Let's go ahead and get our calculator set up. So I'm at negative 33.5. I'm going to go up by 10, so plus 10. I'm going to go up to negative 23.5, maybe right here. And I'm going to use a constant slope because I have a constant shear. Same kind of thing that's over here. I have a constant load, I have a constant slope, I have a constant shear, I have a constant slope. This line reminds me that at this point I have another concentrated moment. It's counterclockwise, so it's minus 3. I go down to 26.5, just straight down. So this negative 23 goes with that point, negative 26 goes with that point. Then I get add, so it's positive, so it's got a positive slope. I add 10, it's negative 16.5. And these slopes here, these two, they should be parallel. If you've drawn everything, relatively to scale, these should be parallel because they have the same shear force that's creating them. So it's 5 kips all across here. So even though they're broken by the concentrated moment, they should be parallel slopes. Now I'm going to go up another 10.5. So I'm going to go up to -6, which is, maybe right here. This one is not a straight line. I have a positive, so it is a, upward slope, but it is getting less steep. So it starts out at 5 and it goes down to 2. So it's going to curve something like that. It's not a big curve, mainly because it doesn't go all the way to 0, so it doesn't flatten out horizontal, but it does have some curvature to it. And then this last little section has a +6. I'm at -6. So should do something like that. Should have continuity at these points. I have a little bit of a change in inflection there, but that's okay. So here's our bending moment diagram. Now, if all we wanted to know was the maximum bending moment in the cantilever beam, we didn't really have to do this because it's going to be the one at the wall. If it's a true cantilever beam where it's not supported anywhere else, then that maximum bending moment is going to be right there at the wall. But I just wanted to draw the whole thing so you know what it looks like and have another sample of how to do that. So let's say we're trying to find maximum flexural stress. We have I somewhere, 863.87. We have M, -33.5 kip feet. We have Y, we haven't talked about it, but on this chart we would have a value for Y. So we've got our composite beam, and we can either measure from the neutral axis, let's see, maybe right here, down to the bottom of the beam would be one location for a maximum stress, or we could measure here to the very top, in this case the very tip top of the channel, for another maximum stress. One of them will be tension, one of them will be compression. This beam is cantilever bending downward, so the tension's actually on top of the beam and the compression's on the bottom, and you can tell that because we have negative bending moments everywhere. They're all negative until they get to 0. So they're all negative. Negative bending moments put tension on the top of the beam. All right? So we need to see which value of Y is larger. Is it the 7.98 or the negative, technically negative 7.98, or is it from neutral axis up to the top? So if I go to the very top of the beam, that's 12 plus H was 3.03, and then subtract off the 7.98. That will leave me with this distance, well, that distance, which is 7.053. So the compression on the bottom of the beam is a little bit larger value of Y, so we'll go with that. All right, so this equals negative. M is negative 33,500 foot-pounds, so I just got rid of the kips and changed them into pounds. I don't need these feet in here because all the other things are in inches, so 12 inches per foot. Now I have inch pounds times Y, which was the negative, we're measuring from the neutral axis downward, so negative 7.98. And then divide by I, which we found to be 863.87. And we do the math. Let's see. So we end up with negative, negative, negative. We end up with a negative number, which makes sense because we said it was going to be compression. 33,500 times 12 times 7.98 divided by 863.87, 3,713.5 psi. So that's not a lot of stress for a steel beam. That's well within factors of safety, factor of safety of 10 or so for most steel beams, and even more for other harder beams, stronger beams. All right, so that gives us, starting with a generic cross-section combined with a store-bought cross-section, combined together, find the centroid, find the moment of inertia for the whole cross-section, find the maximum bending moment, and then find the maximum flexural stress. So this maximum flexural stress is, if this is our beam, cantilevered off at the wall here, then it's right down here. Whoops, the beam fell apart. So if we're cantilevered here, that maximum flexural stress is right here in compression. Some materials behave differently in compression than they do in tension. Most ductile materials don't, though, so most steels don't behave any significantly different way in tension versus compression, but other materials are very different in tension and compression. If this was a concrete beam, it is very different in tension and compression. Actually, it's much stronger in compression. Okay, next time, tomorrow, what we'll do is we will work on what's called design of beams. So if we have a beam, what kind of cross-section does it need in order to have a given factor of safety against all these loads we've put on it? So we'll go through that. It's actually a pretty simple process, and we're only going to use standard beams in charts, like that one. Like that one. So maybe we would pick the C beam that would best suit our loading configuration, or the I beam, or the whatever type beam, and we'll use this section modulus S that's in the column, kind of in the middle. All right, so that's next time. I will see you then. Let me know if you have any questions, and I will try and answer them. But I'll see you tomorrow.